Hello, this is the solutions for test 2 kinematics and dynamics version 1. So let's get started. Question 1. A ball is thrown vertically upwards at the highest point of its trajectory. What are its velocity and acceleration? So we need to know what the velocity is and the acceleration. So this is projectile motion. At the very height, at the top of its trajectory, the ball momentarily has a velocity of 0. It has stopped moving upwards and it has not yet started moving downwards. So its velocity is 0 in that instant. Now the entire time it's in the air, it has a constant acceleration of 9.8 meters per second squared downwards due to the acceleration of gravity. So that was question 1. Question 2, for the ball in question 1 that is thrown vertically upwards, draw the corresponding displacement, velocity, and acceleration graphs for its motion. So I know I'm going to have 3 graphs, and I'm told to not forget the label of the on all of my axes with units. So I will start by doing that for time. And here I will do displacement in meters, velocity in meters per second, and acceleration in meters per second squared. So that part is done. I must place a 0 on the y-axis of every graph as well. You could see the next page as an example, but we won't do that in this video. We're going to hit that next page anyway. And I gave you some space below, plenty of space to do your graphs. So for the position time graph, I'm going to say the beginning of the throw is 0 meters. And this throw, it's going to start going upwards, and it'll slow down, and then eventually it'll start coming back down. And it'll be a parabola, modeling the distance and time here. So that's everything I was looking for a single graph. So let's do the velocity time graph for this. Velocity. It's going to start positive. So it's going to start somewhere up here, some positive velocity going upwards. I'm calling upwards positive here. And then the velocity will decrease over time until it hits the peak where the velocity is 0. And then when it's coming back down, it's going to speed up and become more and more and more negative over time. Speed up in the negative direction. So this is about what the graph is going to look like. Let's draw it for real. And it'll look something like this. And as I mentioned earlier, this is acceleration due to gravity. It is constant acceleration at negative 9.8 meters per second squared. You did not have to put the negative 9.8, but we can, so I am. And this was everything I was looking for questions 1 and 2. Fairly straightforward, I hope. Question 3. Now, this example had that 0 on the axis here. This is what I was talking about. Of course, this graph is much more marked up, complex, has many more elements than what your graphs were required to have. So anyway, question 3, given the velocity time graph below here, complete parts A and B. Okay, part A, calculate the total displacement. All right, let's do that. I'm going to just divide this in half here. I'm going to do part A on the left, part B on the right. So for part A, I know that total displacement is going to be the area between the graph and the 0 axis, the 0 line. So I see a triangle here, a triangle here, a triangle here, a rectangle here, and a triangle here. So I'm going to call that area A plus B1 plus B2 plus C plus D. I'm going to say that all 5 of those areas added together is the displacement. I know this because area on a velocity time graph gives me displacement. Plugging this in, I need my formula for area of a triangle, which is 1/2 base times height. So 1/2 times the base of A, which goes from 0 to 10. So the base is 10. The height is 0 to -5. So this is -5 plus B1, which is going to be 5 is the base, -5 is the height. B2 is going to be 5 is the base, +5 is the height, and running out of room here. So I'm going to start a second line, plus, now this is C, area of a rectangle, so it's just base times height. Our base is 15 times the height of 5. And lastly, adding on the last triangle here for D, base is 5, and the height is 5. Adding these all together, I get -25. Both halves of B actually perfectly cancel out. Add 75, add 12.5. Add all those together, you get 62.5. So therefore, my total displacement equals 62.5 positive meters. So 62.5 meters in the positive direction. That could be north, that could be south, that could be east, that could be west, that could be up, that could be down, that could be left, that could be right. Doesn't matter. Whatever you want it. It's just the positive direction. So that was it for 3A. 3B was calculate the acceleration for each segment of the graph A, B, C, and D. So we need the acceleration for each part. I'm going to break it up like this. A, B, C, D. There we go. A, B, C, D. And I'm going to say that acceleration is equal to y2 minus y1 over x2 minus x1. This is because on a velocity time graph, the way you get acceleration is by finding the slope. So I'm going to take the end point of each line and calculate the slopes. So for A, I'm going to have -5 minus 0 over 10 minus 0, which is going to give me an acceleration of -0.5 meters per second squared. So that is my answer for A. For B, I'm going to have 5 minus -5 over 20 minus 10. This is going to give me an acceleration of +1 meters per second squared. C, this is actually a horizontal flat line. So there is no acceleration here. The velocity is not changing at all. It is constant during C. So acceleration is 0 for this part. Lastly, for D, I have 0 minus 5 over 40 minus 35. Plugging that in gives us an acceleration of -1 meters per second squared. And that is what I was looking for 3B. Question 4, again, relative to the graph here. What is unrealistic about this velocity time graph? A little guiding extra question there. Why is this graph not possible to get in the real world? Just worth 1 point here, this little concept question. This is because the points are sharp. I'll put those in quotations. What does that mean? That means that right here, and right here, these points are sharp. It is not possible for anything with mass in the real world to instantly change direction and velocity, to jump from negative, here we are at -5 meters per second going in the negative direction. Our velocity, we are accelerating in the negative direction along A, and then all of a sudden, instantly we start accelerating in the negative direction for B. These corners should be curved. So, cannot instantly accelerate / decelerate this must happen over some amount of time. So that's what that was. Just worth 1 point, one small little part there. So that was questions 3 and 4. Question 5, using Newton's laws, explain the following. Part A, when you push a shopping cart, why does it move and you do not? So, a couple of reasons here. The force of friction between your feet and the ground the force of friction between your feet and the ground is greater than the reaction force the shopping cart exerts on you. This is due to your greater mass and inertia. It's due in part of your greater mass and inertia. So as you fill up the shopping cart, why does it get harder to move? You are increasing its mass and therefore its inertia also increases. So, part C, describe the motion of the shopping carts if you push the empty shopping cart. Describe the motion of the shopping carts if you push the empty shopping cart and the full, shopping cart with the same force. So, empty cart will accelerate faster because it has a smaller inertia. And the full cart will accelerate slower because it has greater inertia. Part D, leaving the shopping carts behind. Why do you feel heavier than normal when you are on an elevator that just started moving upwards? So, little diagram here quick. Elevator, you're inside. It is accelerating upwards, and it also has a velocity going up as well. You are stationary. So what is happening here is your force of gravity acting on you has not changed. It's staying the same. Despite how you move, force of gravity acting on you remains the same, close to the surface of Earth. But what is changing is the applied force pushing up on you. So the elevator is pushing up on you with an applied force. The normal force is also pushing up on you. And because of this applied force pushing up on you, you feel heavier. So it is the addition of the upwards applied force acting on you from the elevator that makes you feel heavier. I forgot the A. Heavier. There we go. Okay, so that was question 5. Question 6. A swimmer can swim at 2 meters per second relative to the water when she swims directly across a river perpendicular to the current. So I'm going to say the swimmer. Swims directly across like this at 2 meters per second. And she is observed from the shore to swim at 2.8 meters per second at a 45 degree angle. Downstream. Okay, so her relative speed to the shore is 2.8 meters per second. Find the speed of the river's current. So we want to know velocity of the river equals question mark. So we know that the river is flowing to the right here. Flowing to the right. And if the swimmer is swimming directly across the river, perpendicular, but an outside observer sees them swimming at some angle, we know that the river has to be pushing them. The water has to be pushing them. So, first things first, in any one of these types of questions, we want to break vectors into components. In that case, that is our velocity as seen from the shore of 2.8 meters per second at a 45 degree angle So breaking this into components, I have 2.8. This is 45 degrees. Breaking into components, the x and y, I will call them. So Vx equals Vy equals, so this is V sine theta, V cos theta, where V is 2.8, theta is 45. You end up getting 1.98 meters per second for both. Now, what you should notice is that this here is the only x component. For everything. We know that the velocity of the water, of the river, is in the x direction. So therefore, VR has to be equal to the x component of the swimmer's velocity as measured from the shore. So the speed of the river is 1.98 meters per second. And we are just asked for speed. We do not need to give a direction. If we were asked for velocity, we would just say 1.98 or 2 meters per second downstream or in the x direction. Something you could have noticed right off the bat as a bit of a shortcut is that this is a 45-degree angle in a triangle with 45-degree angles here and here. You know that your two side lengths, I'll mark them with x's here, have to be equal. Actually, I'll call them x and y. They have to be equal. X equals y. In our problem here, you are given a triangle with these side lengths. Right off the bat, you know that the other side length has to be a 2. And from there, you can jump straight to saying that VR equals 2 meters per second. So you did not have to do any math at all for this question. If you realized this fact, if you did, good for you. A couple people did. Just from the symmetry of the problem, seeing that it's a 45-degree angle, you know that the current has to be equal to the speed of the swimmer. It has to be equal to it. So there was a bit of a shortcut there, but you could go through and do all the math if you would have liked. So that was it for question 6. Question 7. A 5-kilogram block is sliding up a rough incline. That makes an angle of 25 degrees with the horizontal. The block is initially moving up the ramp at 3 meters per second, but an applied force of 20 newtons continues to push it up the ramp. The coefficient of kinetic friction between the block and the surface is mu k equals 0.3. Part A, draw a free body diagram of the system. Okay. So I have my block. It's on some angle. I have a force of gravity. I have a force of friction pointing down the ramp because the applied force is pointing up the ramp, and we are told that the velocity is up the ramp initially, and it's on the ramp, so we have a normal force. So that was it for the free body diagram. 4 forces, half a point each. Part B. Determine if the block will accelerate, decelerate, or move at a constant velocity. So first I'll show that there was a bit of a shortcut for this question. We know that to figure out if it's accelerating, decelerating, or moving at constant velocity up and down the ramp, we need to find the net force, F net, in the x direction, so up and down the ramp. And that's going to be the applied force plus the force of friction plus the force of gravity in the x direction. Applied force, we're told, is 20. Force of friction, we'll have to calculate. Force of gravity in the x direction, we'll have to calculate. So first, let's calculate the force of gravity in the x direction. That's going to be equal to Fg sine theta, which is going to be 5 times 9.8 times the sine of 25, which is going to give us 20.71 newtons, Fgx. Now, you could have stopped here, because this Fgx is larger than the applied force. So it doesn't matter if there is friction at all. The force of gravity alone is larger than the force pushing it up the ramp. So the block will therefore decelerate. And that was enough to solve the problem. But if you did not catch that, you could have gone and also calculated the force of friction by first finding the y component of gravity, in largely the same way as you found the x component. This was 44.41 newtons. And because this is the only force acting in the y direction that is not the normal force must be equal to it. And then we can go ahead and calculate the force of friction, which is mu k times the normal force, 0.3 times 44.41, which gives us about 13.323 newtons of kinetic friction. Putting this all together into F net, we get 20 minus 13.323 minus 20.71 gives us about negative 14.033 newtons. Finding the acceleration from this in the x direction, you take F net x divided by the mass. This gives us negative 14.033 divided by 5. The acceleration is negative 2.8 meters per second squared down the ramp. Therefore, it decelerates. So, could have gone through and done all the math. There was a little bit of a shortcut in this question, though. As soon as you found Fgx, you could have noticed that it was larger than the applied force, and that alone would be enough to make the block slide or slow down, come to a stop. So it will decelerate. Question 8. A cannon fires a cannonball with a speed of 60 meters per second. So I'll say VI equals 60 meters per second at an angle of 35 degrees above the horizontal. Above the horizontal, that's what AH is going to mean. The cannonball lands at the same height it was launched from. You may use extra paper if needed. That's just in case you wanted the extra space. Here. Part A, find the maximum height of the cannonball. Part B, find the range of the cannonball. Part C, find the total time of flight of the cannonball. So I'm going to, once again, break up my paper into sections here. All right. Part A, maximum height, we use our Y max formula. So this is going to be 60 squared sine squared 35 over 2 times 9.8. It's going to get you about 60.4 meters. There we go. For the range, we can use our range formula. This is the one with sine 2 theta. Plugging in numbers, we get 60 squared sine of 2 times 35 over 9.8. This is going to give me 345.2 meters as my range. Oh, lastly for C, total time of flight. Lastly, we use our time equation for this scenario. Guess I should be keeping my subscripts. Sine theta over g, plug in 2 times 60 times the sine of 35 over 9.8. We get a time of almost exactly 7 seconds, and we'll round it. So that was questions 7 and 8. And I believe the last question here, yes it is, question 9. A bit more complicated. So, writing out my givens first. We have a mass of 0.4 kilogram ball. It is launched horizontally from a spring launcher that applies a force. So I have an applied force of magnitude 69.5 newtons. While friction, okay, so I have a force of friction, provides a force of magnitude 8 newtons of resistance. The ball accelerates along a 0.25 meter track. So I will say delta D equals 0.25 meters. Excuse me. I will say X. Then leaves the launcher from a 1.5 meter high table. So we'll call this H, 1.5 meters. A target 1 meter above the ground is placed 2.8 meters away. I'm going to write that out separately. So this is for the target. Delta dx equals 2.8 meters and h equals 1 meter. So that is for the target by itself. We're going to treat that one differently by itself. I'm going to change that color to pink or something, just so it's a little different. Sorry if you're colorblind. I don't think any of you are. Okay. So, and we're asked, will the ball hit the target? So we need to know if the ball has a height of 1 meter after it has traveled horizontally 2.8 meters. Okay. So first, to do that, I know I'm going to need to know how fast it is launched, its velocity. I'm not told that, but I am told about the forces involved. So first, let's find the net force on this ball. So, and that'll be in the x direction because it's not moving in the y direction yet. So net force, I'm going to take my applied force, subtract friction from it. That gives me 61.5 newtons as my net force. We can use F net equals ma to calculate acceleration. We get 61.5 over 0.4. This is going to give us an acceleration of 153.75 meters per second squared. Okay, great. So I have an acceleration. I know it is accelerating at this rate. I also know that the track is 0.25 meters long. So I know the acceleration and I know how long it accelerates for. Let's assume that the initial velocity equals 0 meters per second. Let's assume that this is launched from rest. So final velocity, the launch velocity, is going to be equal to vi squared plus 2a delta d all square rooted. Our initial velocity, that's 0, so we can cancel that out. So this is going to be 2 times, not 9.8, which I almost wrote. This is going to be 2 times the acceleration we just calculated, because we are working in the x direction right now. The track is 0.25 meters long. So this gives us a final velocity of 8.77 meters per second. Now this becomes our initial launch velocity. Launch velocity. Okay. So I'm going to write this as VI equals 8.77 meters per second to the right. This is my initial launch velocity. So now I am going to find the time it takes to get to the target. This is projectile motion. So we know that horizontal and vertical components are independent. They are separate from each other. So I can say that there is 0 acceleration in the x direction. That speed will be constant. Because of that, I can use this formula I've written in black, where time equals distance over velocity. So I'm looking for the time it takes to go 2.8 meters, the full distance to the target, at a speed of 8.77 meters per second. This gives us a time of 0.32 seconds. So I know it takes 0.32 seconds to get to the target. Now let's find the height at the target. So the height at the target, h, is going to be equal to 1.5, because remember this was launched off a 1.5 meter high table. So I need to add that into the calculation, plus the initial y velocity multiplied by time. I'm going to erase this arrow for now. Plus 1/2 times the acceleration in the y direction times time squared. And plugging in some numbers, the initial velocity in the y direction is 0. Remember, this is launched horizontally. That is y. That means that the initial velocity in the y direction is equal to 0. It's not launched up or downwards, so the initial velocity in the y direction has to be equal to 0. So we can ignore that term. Great. This is 1/2. Now the acceleration in the y direction. This is the acceleration due to gravity, not the acceleration we calculated earlier. And the time was 0.32 squared. Putting this all together in a calculator, I got 0.99824 meters. Now this is a real target. It's not a single infinitesimally small point. If it was, then of course it would miss, because this isn't exactly 1 meter. But I will round this up and say that h equals 1 meter at that time. So therefore, it hits the target. And there we have our final answer to this problem. And that was the whole test. Thank you for watching.